Welcome to Theory of Computation. This is lecture number 17. In the last lecture, we studied Pressburger's arithmetic. That was actually number theory without multiplication. So in Pressburger's arithmetic, you were able to make formulas which use the symbols plus but not multiplication. And you could make formulas which were quite complicated using Boolean connectives, ands, ors, and nots. And two quantifiers, they exist in for all. What we showed was that Pressburger's arithmetic is decidable in the sense that we can have a Turing machine, an algorithm, to which you can give as input a statement in Pressburger's arithmetic, and the algorithm will tell you whether that statement was true or not. The algorithm was quite complicated. It was actually an extremely non-trivial application of DFAs. The theory of DFAs was used to show that the Pressburger arithmetic is decidable. What we showed was that DFAs were powerful enough to capture any formula written in Pressburger arithmetic. The decidability of Pressburger arithmetic has many non-trivial applications, especially in automated theorem proving. I would encourage you to Google on Pressburger arithmetic and find out a lot more about it. So we were able to show that there was a model whose theory was decidable. Today's lecture is going to be very different. Today we are going to look at much more powerful models. And what we will see is the theory of those models is not decidable. So today's lecture is going to be about undecidability of logical theories. Let's look at the overview of today's lecture. We will today discuss the undecidability of logical theories. In particular, we will first define piano arithmetic and then show that statements in piano arithmetic cannot be decided by Turing machines. The last part of this lecture is going to be a proof of Gödel's incompleteness theorem. Well, yesterday we looked at three statements that motivated our discussion of logic and models. Let's have a look at those statements once again. The first interesting statement was, well, if we read it the way it's written, it says for all q there exists p, said that for all x, y, p is greater than q and x, y greater than 1 implies that x times y is not equal to p. If we read this statement in English, this statement simply says that there are infinitely many primes. This is a very interesting statement. The second statement said that a to the n plus b to the n equals c to the n has no solutions in positive integers as long as n is strictly greater than 2. This is known as Fermat's last theorem. This is also an extremely interesting statement, and mathematicians spent a lot of time proving this statement. The last statement says that there are infinitely many twin primes. That is known as Goldbach's conjecture. As you can see, these statements are not statements in Pressburger arithmetic because the first statement uses multiplication. It says x times y is not equal to p. So this is not allowed in Pressburger's arithmetic. So this statement is not a statement in Pressburger's arithmetic. Similarly, the second statement uses exponentiation, which is not a part of Pressburger arithmetic. And the third statement also uses multiplication, and therefore it's not a statement in Pressburger arithmetic. However, these statements are extremely interesting. So now what we want to do is discuss a model in which these statements can be expressed. We want to discuss a model such that these statements are in the language of that model. Let's look at that model. The first two of these statements use multiplication, and the second also uses exponentiation, which is not allowed in Pressburger arithmetic. Let's now study a different model. This model is going to be n plus n multiplication. In this model, the universe is the set of all integers, and we have times and plus as relations with their usual meaning. The first and the third statements are in the language of this model. This, to many mathematicians, is the most interesting model. It is what we call number theory or piano arithmetic. So, statements in number theory or piano arithmetic, or this particular model which we denote by n, plus and cross, can have multiplication in them. Of course, they have the usual logical connectives and, or, and not, and we will allow quantification. Let's continue. The most important question is the theory of this model decidable? Note that if this was the case, we would have an algorithm which could decide if Goldbach conjecture is true. Such an algorithm would be amazing. It could tell us about the truth or falsehood of many mathematical statements that we are interested in. So, if this theory were decidable, and we were able to find an algorithm which decided this theory, we would simply program that algorithm in a computer and then give it Goldbach's conjecture as an input and sit back. And we'd be sure that one day that algorithm will output true or false, telling us whether the Goldbach's conjecture is true or whether it is not true. So it would be very nice if this theory were decidable. We will prove that this theory is not decidable. The theory of n plus and cross is not decidable. In one sense, it is bad, and in another, it is good. This shows that no algorithm can be devised that can decide the truth and falsehood of general statements in number theory. Why is that bad? Well, because proving statements in number theory is not a mechanical process. We cannot write a program which does that. On the other hand, it is interesting because when we work on a statement like Goldbach's conjecture, we are sure that no computer can be devised that can solve this problem in general. So we can at least tell ourselves that we are doing something creative. So this number theory not being decidable is bad news because we don't have an algorithm, but it's good news because we can take number theory as a profession. Let's continue. In order to prove that number theory is not decidable, we will need this auxiliary theorem. This theorem says that let M be a Turing machine and W be a string. Then we can construct from M and W a formula phi sub M of comma W. So this formula will depend on M and W in the language of number theory such that there exists X phi of M comma X is true if and only if M accepts W. So if we have a Turing machine M and we have input W, by looking at the Turing machine and the input, we can come up with a formula phi, which will of course depend on M and W, such that this formula is true if and only if M accepts W. So we can express the fact whether M accepts W in number theory. The proof of this theorem is quite large and complicated. To make the proof a bit simpler, we have provided the proof of the following theorem in the handout. This theorem that we are going to prove is going to be slightly weaker than the one that I have stated. In number theory, we have two operations, plus and multiplication. What this handout given to you shows is that if you have the operation plus, multiplication and exponentiation, then we can construct such a formula in the language of that theory. So it's slightly weaker. However, it has all the ingredients that are needed. The proof is very technical and it has a lot of technical details. So we're just going to briefly discuss the proof in this lecture. So the theorem we want to prove is let M be a Turing machine and W a string. We can construct from M and W a formula phi of M comma W, and this is going to be in the language of number theory with exponentiation such that there exists phi mx is true if and only if M accepts W. Notice that the statement of this theorem is the same as the previous one, except for now our model allows us to use exponentiation. Even this is quite technical to prove, so the proof is included in the handout for interested students. We will only discuss certain aspects of this proof. So I will tell you a bit about what are the techniques and what are the main points that are used in this proof. The basic ideas used in this theorem are that the formula phi sub m comma w says that x is an accepting computation of m on w. So what we do is we construct a formula which says that x is an accepting computation history of m on w. If we can do that, then there exists x phi of m comma w would be true if and only if m accepts w, because m accepts w if and only if there is an accepting computation history of m on w. On the other hand, if m does not accept w, then this formula is not going to be true, because no computation history will be an accepting computation history of m on w. That's what this formula tries to express in the language of number theory. The second point is the operation times, plus, and exponentiation are used to extract symbols or chunks of symbols. So if you have a computation history which is just configuration followed by another configuration followed by another configuration, you can think of this computation history as a large number which is written in some large base. The base would be as large as the number of states in the machine plus the number of work symbols and so on. But you can read it as a number. And using exponentiation, you can extract various parts from this computation history. And then we use multiplication and plus to compare them. So we compare one configuration with another one and see if one of them yields the other one. And this requires that we look at the Turing machine M, so the formula depends on M, and it also requires us to look at the initial input, and so the formula depends on W. Let's use this theorem in order to prove the theorem that we really want to prove, which is that the theory of n comma plus and cross is not decidable. Using the previous theorem, we can now prove that the theory of n plus and cross is undecidable. The proof is we will reduce ATM to this set. Recall that ATM is the set of all pairs m comma w such that m accepts w. So all we have to do is reduce ATM to this set. In order to do that, we give a mapping reduction which is given as follows. On input m comma w, construct this sentence which is guaranteed by the previous theorem. There exists x phi sub m comma w, and output it. Clearly, the previous theorem says that m accepts w if and only if this sentence is true. Thus, m accepts w, which means that the pair m comma w is an ATM if and only if this sentence is in the theory, because this theory contains all sentences which are true. So, what we have done is found a reduction. We have reduced ATM to this theory. Since we know that ATM is undecidable, therefore this theory is also undecidable. This is a very important statement, that there cannot be an algorithm that takes a statement in number theory and tells us whether this statement is true or false. We are now in a position to prove an extremely celebrated theorem of Kurt Gödel. Gödel was a German logician, perhaps the greatest in history. Here's a picture of Gödel. Gödel proved a theorem that simultaneously shocked and delighted the mathematical world. What Gödel was able to show that there are mathematical statements which are true, but which we will never be able to prove because they are not provable. In the sense, there is no proof in the world that you can find which will tell you that that statement is true. But these statements are true. This was an extremely shocking and delightful theorem. Let's have a look at what Gödel's theorem says, formalize it, and try to prove it. Gödel's theorem started with one of Hilbert's idea. Hilbert actually proposed a program. His program was to bring all of mathematics to a sound foundation. what Hilbert was trying to do is to take all of mathematics and put it on a foundation such that it would be extremely sound and formal. He wanted to formalize all of mathematics, how people do mathematics, how they prove things, and everything about mathematics. So he said that what we should do is prove the following things about mathematics. Number one, he wanted to formalize all mathematics. All mathematical statements should be written in a formal language and manipulated using well-defined rules. What Hilbert meant by well-defined rules was something like this. Suppose that I tell you that A implies B, where A is a mathematical statement and B is a mathematical statement, and I tell you that A implies B. And then I also tell you that A is true. Well, from there we can conclude that B is true. This rule is called modus ponens, and it is always used in mathematics in almost any proof. But this rule can be formalized. We can say we are always allowed to use these rules. Well, there are other rules like that we use in mathematics. What Hilbert wanted was to make a complete list of all those rules of logic, which would be used to do mathematics. And when we wrote our proofs, we would only use those rules which were allowed in mathematics. We should be able to come up with a complete list of what are the rules for doing mathematics, what is the exact syntax of those rules. The other thing that Hilbert required was to show that mathematics is complete, which means to prove that all true mathematical statements can be proved. So Hilbert had offered a very big challenge to show that mathematics is complete in the sense that anything which is true in mathematics, whatever can be expressed in mathematics, if it happened to be true, we can find a proof for it. And Gödel wanted a proof of this statement. So, once again, Gödel was asking for a mega proof or a meta proof, which would say that all true statements are provable. This property was called completeness, and Hilbert was interested in showing that mathematics was complete. The next requirement Hilbert had put was to show that mathematics is consistent. What does consistency mean? This means that whatever we prove in mathematics would always be true. We will never be able to prove an absurdity, a false statement using mathematics. A correct proof will only be able to prove a true statement. So, if we had completeness, we would be able to prove all true statements, and if mathematics was consistent, then we'll only be able to prove true statements. We will never be able to prove absurdities. There was another requirement that Hilbert wanted, and that was decidability. He wanted to show that there is an algorithm for deciding the truth and falsehood of any mathematical statement. Hilbert suspected that all mathematical statements could be proved from number theory. So in some sense, he was asking if number theory had satisfied all these requirements. So Hilbert was asking if mathematics could be completely formalized, if it was complete, which means all true statements were provable, if it was consistent, which means we'll never be able to prove absurdities, and lastly, if it was decidable, if we could have an algorithm which would prove any mathematical statement. You could give any mathematical statement to this algorithm, and this algorithm will work for a while, and after that tell you whether the statement was true or not. Well, as you have suspected, Hilbert's program ran into trouble. We have already seen that number theory is not decidable. Therefore, Hilbert's program never reached its end, or it rather reached a premature end when Kurt Gödel showed that mathematics was not even complete, that number theory was not complete. That was Gödel's celebrated incompleteness theorem. This theorem had deep implications on the foundations of mathematics. Let's look at this theorem. Gödel showed that there are statements in number theory which cannot be proved. He also showed that the statement that claims that number theory is consistent cannot be proved in number theory. This showed that Hilbert's program was doomed. Gödel's theorem is considered to be a cornerstone in foundations of mathematics. It is an extremely important work with far-reaching consequences. So, Hilbert's program was abandoned simply because mathematics was not complete. Number theory is consistent. Whatever you prove using number theory is always true. However, there are statements in it which can never be proved. What we want to do is actually prove Gödel's theorem in the rest of this lecture. This is a very important theorem. It's an extremely exciting theorem. So we'll go through the proof very slowly. Let's continue. Let's prove that there are statements in number theory which cannot be proved. In order to do this, we have to define what a proof is. But instead of going into exact definitions, we'll be a little bit informal in our treatment. The exact definitions of what an axiom is, what a proof is, are quite cumbersome. So it will suffice for us to define these things a bit non-formally. Let us start with a set of axioms. Set of axioms are just a set of statements. So for example, the set of axioms for numbers are the following. There are 15 axioms which are written in this transparency. These statements, once you look at them, look extremely daunting. There are 15 of them and they're quite complicated. And these axioms are called Peano's axioms. These are statements that we assume are true about numbers. But actually, once you look at each one of them individually, they are not hard at all. Let's have a look at few of them. The first statement says that for all x, y, and z, x plus y plus z is the same as x plus y plus z. This means that addition is associative. The second statement says that addition is commutative. The third statement says that multiplication is associative. The fourth statement says that multiplication commutes. The fifth statement actually says that multiplication distributes over addition. That is called the distributive law. All these axioms you were taught when you were children. These were properties about additions and multiplications you were taught and told when you were students. They are all the axioms that we have about addition and multiplications. These are called Peano's axioms. Let's once again have a look at a few more of them. The next one says that 0 is the additive identity and anything multiplied by 0 gives us 0. The next one says that 1 is the multiplicative identity. The third one says that the operator less than is actually transitive. X is less than y and y is less than z implies that x is less than z. The ninth axiom says that no number is strictly less than itself. The 10th axiom says that if you have two numbers x and y, then x is less than y, or x is equal to y, or x is greater than y. This is called the law of trichotomy. If you give me two numbers, then I have three alternatives and only one of them happens. The first alternative is that the first number is smaller than the second one. The second alternative is second number is smaller than the first one. And the third alternative is that they are equal. This is called law of trichotomy, and exactly one of them holds. Let's continue looking at these axioms, the Peano axioms. The next axiom says that if x is less than y, then x plus z is less than y plus z. So if you have an inequality and you add the same number to both sides, you preserve that inequality. The next axiom says that if z is greater than 0 and x is less than y, then x times z is less than y times z. So if you multiply an inequality by a positive integer, that inequality is preserved again. These are piano axioms. Let's look at the next axiom. The next one says that if x is less than y, then there is a z such that x plus z is equal to y. So if x is strictly less than y, you can find something that when you add to x, that becomes equal to y. Let's look at the next axiom. That says that 0 is less than 1, and for every x, if x is greater than 0, then x is greater than or equal to 1. So this axiom says that 0 and 1 are different integers, and there is nothing in between these two integers, and all other integers are larger than 1. Let's look at the last axiom. It says for all x, x is greater than or equal to 0, so 0 is the smallest natural number. These axioms are not enough to define all the properties of numbers. We need one more axiom. Let's look at this very, very special axiom. We have to add to this set of axioms this axiom which says phi of 0 and for all x, phi of x implies phi of x plus 1 implies that for all x, phi of x. This is better known as the principle of mathematical induction. The question is, as you can see, here we have not specified what phi is. Here phi can be any statement. This principle of mathematical induction says the following. It says that if you prove a statement is true for 0, so you have a statement about numbers, and you prove that it's true for 0, and you prove that whenever it's true for x, it's also true for x plus 1, then you can conclude that the statement is true for all natural numbers. We use the principle of mathematical induction in our proofs, but it's actually an axiom. It's a property of natural numbers that we assume that they have. It's in some sense a property that natural numbers have by their very definition. This is an axiom. It's a very special axiom. I did not write it with all the other axioms because it's not one axiom. The principle of mathematical induction is a statement about statements. So it is saying that this statement is true and you can replace phi with any statement that you want. So the principle of mathematical induction in some sense is infinitely many axioms. These have to be added to the piano axiom, or the principle of mathematical induction has to be added to the piano axioms, and then we get all the properties of natural numbers. These are called axioms. Now let's go on and see what a proof is. Once we have defined axioms, we can now define a proof. A proof pi of a statement S is going to be a sequence of statements S1, S2 all the way up to SL, such that each SI is either an axiom or each SI follows from the previous SJs using rules of logic which are precise and well defined. Lastly, we will require that the last statement in this sequence should be S, the statement that the proof is saying it's proving. So, a proof is a sequence of statements. The last statement is the one that we are trying to prove, and each one of these statements is either an axiom or follows from some previous statements using rules of logic. One of the rules of logic we saw was modus ponens. So for example, suppose that we are given S and we are also given S implies T, then we can conclude T. Note that this rule is purely syntactic in the sense that we can have a computer check if this rule was applied. It does not need any intelligence to check whether if S implies T was given and S was given, then T was concluded. This application of this rule is absolutely syntactic and can be checked by a computer. This is a main property of proofs. They can be checked by anyone. That's why mathematicians like writing proofs, because it proves an assertion, and this proof can be verified by other mathematicians. In fact, these proofs can be verified by computers also. With this in mind, we would make two observations. The correctness of a proof can be checked mechanically, that is, via a Turing machine. In other words, the set of all pairs phi, pi said that pi is a proof of phi is decidable. What you can do is you can write a computer program that takes a statement and a proof and verifies if this proof is correct. Because in order to verify the correctness of this proof, all it has to do is syntactic checking. It does not require any intelligence in order to check if a proof is correct. And all it has to do is first of all, check that every step of the proof was correct syntactically, and then check that the last statement, the conclusion of the proof, was actually phi. Therefore, we can write a program which takes pair phi, pi and tells us whether pi is a correct proof of phi, and therefore we say that this set is decidable. The next observation we will make is that if any statement is provable, then it must be true, that our proof system is sound. What soundness means is that using our proof system, using our mathematical proofs, we can never prove absurdities. We cannot prove false statements, that our proof system only proves statements which are true. The soundness of number theory has been shown by mathematicians, and we will take it for granted. Number theory is known to be sound, so we will assume that if a statement has ever been proved using number theory, then it is a true statement. You will notice here that we are making very basic assumptions. These are questions that we have never questioned. We have never questioned the fact that someone can give a correct proof of an incorrect statement. Hilbert's asking these very foundational questions led to amazing developments in mathematics. So, we will start with these two observations. One, that number theory is sound. Two, that proofs can be checked by an algorithm to prove Gödel's theorem. Let's prove this very simple theorem, which says that the set of provable statements in number theory is Turing recognizable. In order to prove this theorem, we will use our previous technique. What we will do is enumerate all possible proofs and check whether they prove the statement that is given to us as an input. So, the proof of this theorem is given by describing a Turing machine. This Turing machine is described as follows. On input phi, enumerate all possible proofs pi 1, pi 2, pi 3, pi 4 and so on, and check if pi I is a proof of phi. If it is, accept. So, if we give this algorithm a statement which is true and provable, a provable statement, since the algorithm is systematically going through all possible proofs, therefore it will eventually find a proof of this statement and halt and accept. On the other hand, if we give this algorithm an input, a statement which is not provable, the algorithm will continue to go through all possible proofs. None of the proofs would be a proof of this statement, so it will run forever and never halt. We will use this theorem in order to prove Gödel's theorem. What we are now going to prove is a version of Gödel's theorem which says that there are some statements which are not provable. This is very important. What we can do is we can find some statements that are not provable. Let's look at a formal proof of this statement that there are statements which are not provable. Some true statements in number theory are not provable. We start by considering the following algorithm. On input phi, we enumerate all proofs pi 1, pi 2, pi 3 and so on. And what we do is first check if pi I is a proof of phi. If it is, we accept. and then check if pi I is a proof of negation of phi. If it is, then we reject. So if you give this algorithm an input which is phi, then the algorithm tries to find a proof for either phi or negation of phi. Every statement is either true or false. So if you are talking about a given statement, either that statement is true or its negation is true. Now if all true statements were provable, then either phi will have a proof or the negation of phi will have a proof. So this algorithm would be guaranteed to halt. So what kind of a set does this algorithm accept? Well, let's look at it. If all true statements are provable, then since each statement is either true or false, hence phi or negation of phi is provable. Thus this algorithm will be a decider for number theory. This is a contradiction since we have already proved that number theory is not decidable. So this algorithm simply tries to find a proof for phi or the negation of phi. If number theory was complete, every true statement had a proof, then what we'll be able to do is decide number theory, which is what we have exactly proven is not the case. So this shows that there should be at least one statement which is neither provable nor its negation is provable. And that shows that there is at least one statement that is true which is not provable. So we have been able to show that some statements must be there which are true but not provable. Of course, we are speaking all in the context of number theory now. Our model is the set of universe is the natural numbers, the operations, relations defined on it are multiplication and addition with their usual meanings. Well, what we have done is shown that there are some statements which are not provable. A very interesting question is, can we actually pinpoint a statement which is not provable? An even more interesting question is, can we actually find a natural statement, a statement that we would want to prove, but which is not provable? Let's now try to actually construct a statement, a particular statement, which we can point to and say, well, this statement is not provable. In order to do that, we will have to use the recursion theorem and other tools. Let's begin with this. The previous theorem just says that there are true statements which are not provable. Can we actually construct such a statement? This is what Gödel actually did. He constructed a statement which was true but not provable. So let us also construct such a statement. We will use the recursion theorem in order to construct such a statement. Recall what we proved in the recursion theorem. Remember, the intuitive description of recursion theorem was that we can have a program that gets its own description and then does some analysis on it. So the recursion theorem allows us to have a call, and a function can, a program can get access to its own description. We will use the recursion theorem. Let's look at the following program that uses its own description. It uses the recursion theorem in order to get its own description and then does something. This program gets W as an input and it obtains its self-description. This is where we use the recursion theorem. Next, it constructs a statement psi which says that there does not exist an x such that phi of s, 0. Remember the statement phi. Phi says there exists x, phi of s, 0 says that s does not accept the input 0. Now this program checks if psi is provable. If psi is provable, then it accepts its own input w. So this program gets its own self-description. Then it constructs a statement that says this program does not accept 0. Then it tries to prove this statement or tries to find a proof of this statement by enumerating all possible proofs. If it finds a proof of this statement, it accepts its own input. Let's analyze what exactly this program is doing. The fourth step of this program can be done as the set of all provable statements is Turing recognizable. Let's clearly see what phi is saying. Recall that there exists phi s, 0 says that s accepts 0. Hence, psi says that s does not accept 0. So, psi is saying s does not accept this statement. Well, this program tries to find a proof of that statement. If it finds a proof of that statement, then it accepts all its inputs. So, in particular, it accepts 0. So, the statement psi is saying that s does not accept 0, and the program will accept 0 if and only if it cannot find a proof of this statement. Well, since this is a statement, this statement can either be true or false. Let's see what happens if this statement is false. Psi says that s does not accept 0. So, if this statement is false, then s accepts 0. However, s will only accept 0 if it finds a proof of psi. But false statements are not provable. That's because we have assumed that our system is sound. Therefore, this statement cannot be false. Hence, this statement must be true. Since this statement is true, that means that s does not accept 0, which means s will not be able to find a proof of it. So, this is a statement which is true but not provable. This is a twisted argument. Let's go through it once again. If s finds a proof of psi, it will accept 0 and all its input. Psi says that s does not accept 0. Thus, if s finds a proof of psi, then psi is false. But false statement cannot have a proof. Therefore, psi is true. But that means s does not find a proof of it, and hence this statement is unprovable. So now we have come up with a particular statement, a statement that we can point to. The description of this statement, in order to describe this statement, we have to use the recursion theorem, and the statement will be very elaborate and complicated. In spirit, this statement just says that the program S does not accept the input 0. This statement is not provable. However, people can argue that this statement is a true statement, it's not provable, but it's not extremely interesting. No one would ever want to prove this statement. So, there is another challenge. One challenge was to come up with a statement which is interesting to mathematicians, which has consequences in mathematics. That was true but not provable. Gödel even rose to that challenge. He actually showed that an extremely important statement in mathematics, an extremely important statement which we want to prove in mathematics, is not provable. And that statement is the following. Gödel showed that number theory can never prove its own consistency. Remember what consistency is. A system is called consistent if all the statements that can be proved in that system are true. Roughly speaking, a system is consistent if the system does not allow us to conclude absurdities. So, we'd be very interested in knowing if using number theory we can ever reach absurdities or not. And what Gödel showed was number theory could not prove its own consistency. A statement which we would want to prove did not have a proof in this model. That is Gödel's second incompleteness theorem. Gödel proved that the theory of numbers cannot prove its own consistency. These two theorems of Gödel's are extremely important cornerstones in mathematical logic. They changed mathematical logic completely, and they also gave wonderful directions to computer science, to the theory of decidability and undecidability in logic. The way we have gone to prove Gödel's theorem is using Turing machines, using the recursion theorem, using all the tools that we have learned in this course. However, Gödel's original proof of incompleteness was not based on these ideas. Gödel actually followed a very different route. What he did was he actually came up with the idea of numbering statements. He argued that every mathematical statement in number theory could be assigned a number. So you could talk about the first statement, second statement, third statement, fourth statement, and so on. You could list all the statements and give them a number, the so-called Gödel number. Then he said that these statements in number theory, which can only talk about numbers, can indirectly talk about other statements. So a statement can refer to another statement by using its Gödel number. Then he actually used some very elaborate diagonalization to come up with a statement which, when read appropriately, said, "I am not provable." Well, then he gave the following brilliant argument. He said, let us look at the statement which says, "I am not provable," which should be read properly as, "I am not provable in this model," or "I do not have a proof in number theory in this language." Once he came up with that statement, he said that such a statement must invariably be true. And the reason for it was the following. Suppose that the statement which says, "I am not provable," is not true. Then since it says it's not provable and the statement is false, therefore this statement would be provable. But if number theory is consistent, then all provable statements are true. Therefore, that would force the statement to be true, which is an absurdity. Thus, this statement had no choice but to be true. The statement could be only true. Now, if a statement which says, "I am not provable," is true, then surely it's not provable. That was original argument of Gödel. The way I've described to you this argument, it seems very simple, but there are lots of technical hurdles that Gödel had to overcome in order to construct his proof. If we go into the original proof of Gödel's theorem, we will have to learn a little bit of number theory, actually a reasonable amount of number theory, and we'll have to study mathematical logic in detail, which is not the subject of this course. However, I would urge you to do a Google search on Gödel's theorem and read more about it. It's a fascinating subject. It's a fascinating theorem in mathematics. You would be able to find a lot of information on Gödel's theorem and its consequences. Not only that, you would also be able to find Gödel's original proof of his theorem and its translation. That proof is, and that paper, the original paper of Gödel which proved the incompleteness theorem, is extremely readable. It would be very nice if you could try to read that proof and see the brilliance of Gödel that he shows in that paper. I will see you next time. Thank you and goodbye.